Welcome everyone to this first class on complex systems and non-equilibrium kinetics. My name is Thomas Hermans. You can contact me on this information below. Here's my email, Twitter, or you can go to our website for more information. So the resources for this course, I highly encourage you to write along on a notebook, so pen and paper or tablet if you're more digital, but really try to follow what I'm writing, not for this course, for this first course, but you'll see in the following courses, a lot of it will be on the blackboard or whiteboard. So try to follow along. It's a good exercise to better understand how kinetics works. It's really, you have to put in the work to get to understand it. Make sure you check out the Moodle page, but you should. If you're watching this video, it means you found the Moodle page. So I will communicate everything related to the course via Moodle. I will use a number of books. So if you want to read in more detail about some aspects of this course, you can have a look at these 4 books. They will go in way too much detail for what we're going to go through in this course, but if you are really interested, you can check out those books. So let's start with the definition. So chemical kinetics, what are we going to look at? It's basically looking at rates. How fast does a chemical reaction proceed? And it's quite different to the field of thermodynamics, which tells you which reaction can occur and in which direction it will occur, but it does not tell you much about the speed or the rate of the reaction. As we'll see, however, now thermodynamics and kinetics are quite intertwined, and there are quite some thermodynamic aspects that are now considered also in kinetics. So how did this all start? And we're going to start way back before chemistry was even a well-established field, right? So before chemistry, there was something called alchemy, and alchemy, they realized that there were a number of elements. So for example, this upside down triangle here is water. So they had an idea of different elements that would exist, but they didn't know exactly the chemical composition. And so the process of the development of kinetics is basically a story of how we go from alchemy to modern chemistry. And this is a little bit similar to how physics went from natural philosophy to modern science, to Galilean science. And so during the 17th century, this alchemical concept was developed, and one of the first people to work on that was William Homburg, and he developed a concept called a chemical wedding. And that means that similar substances, they will react, so we can categorize them. So the real innovation was that this was not just a naming principle, but really to start understanding chemical reactivity, and so that if there are 2 substances and they are similar, there's a base for reactivity, and thus that's a kind of early predecessor of chemical affinity, which started kind of as an intuitive principle, but it really became more of a theory, first qualitatively, and then later, as we'll see, quantitatively. So in the so-called opera of alchemy, there were transformations of metals. Of course, you know that one of the goals in those times was, how can we convert any metal to gold, which we of course now know that that's not really possible. But at those times, they were trying to achieve that as a major goal. But then there was Wilhelm Homburg. He was a German scholar. He worked in Magdeburg in Germany, and later in Italy and in England. with Boyle. I'll tell you a story about Boyle in a second. But he was basically the first one to introduce a quantitative measurement of a chemical reaction. So he looked at the strength of acids towards a number of alkali and looking at the time of neutralization of these different alkali. So Homburg, he worked with Robert Boyle. I just want to tell you a little story about Robert Boyle. I mean, he has nothing to do with chemical kinetics, but he was basically one of the first ones to start practicing modern science. And so it was a split between religion, because before that time, let's say before the 17th century, everything that happened in the world had to be explained by God in some way. So Robert Boyle, he on the right side here, you see his first invention, which is an air pump. So he has this ball here, which is a chamber, and then he has some kind of pumping device here. So he was the first person that we know, at least, that made a vacuum. And so this is a famous painting by Joseph Wright of Derby. So this is a depiction of one of these experiments of Boyle. So here you see the glass, container. In this case, there's a bird inside. You can imagine if you pump out the air, the bird will not be very happy. So the bird dies. And so Boyle basically described a number of these experiments in the air pump. So for example, putting two fans, if there's air in the chamber, if you turn one fan, the other one will turn as well. If you then produce a vacuum, the other fan no longer turns. So Boyle was describing a number of these experiments, and that was done in a kind of on a stage. There was an audience. So you see here in this painting, there are people around that were witnessing these experiments. And these circumstances led to the founding of the Royal Society of England, the RSC, right? Royal Society of Chemistry, Royal Society in general. And that was a very important point in time, because it was a place where these crazy scientists could do their experiment and not interfere with the religious aspects. So I think that was really a turning point in modern history to develop science as a general thing. So there's a very interesting book. It's called Boyle and the Air, or no, Leviathan and the Air Pump. So if you are more interested in this kind of history, you can read that book. So here you see Etienne François Joffre, and he was initiated to chemistry by Homburg himself, and he produced a first thing that starts looking like some kind of periodic table. It was called the table of affinity. So in the first row of this table, you can see the substances, and going down the columns, you see similar substances, but that have a different order of affinity with the first one. So if you paid attention on the previous slide, this upside down triangle, this is water, for example. So a bit later came Louis Bernard Guiton de Morveau, and he basically was the first one to classify different kinds of affinities. So he called it simple or aggregation, composed, decomposed, double, reciprocal, intermediate. Anyway, he was the first one to realize or really work out more details of affinity, and he also listed some of the first laws of affinity, very qualitative, right? So he said molecules have to be in the fluid state. That means, if you want to have reactions, of course we know now that you can have solid state reactions, but on reasonable timescales, at that time, people were only looking at fluid state reactions, and most of chemistry still today is done in the fluid state, so that kind of makes sense. That affinity acts between elementary particles, okay. They can be different, fine, and only a substance will react if its affinity is larger than the affinity of themselves. So it basically says that substances react only with a compound that has a higher reactivity. Then this is kind of important, right? So if you form a new body, a new substance, you do a chemical reaction, you form a new compound, it has different properties than the precursors. So that clearly shows that they were realizing that chemical reactivity can really lead to new compounds. And then very important, affinity action, so the reaction, and velocity depends on temperature. So already in the 17th century, people realized that reactivity and temperature are intricately connected. So Torben Olof Bergman, a Swedish scholar, he added a little bit more detail on that. I don't have it here on this slide, but he basically suggested that affinity tables should depend on the conditions. So the dry phase, the neat state of a compound, will be different than that of the liquid phase. And so Bergman was the first scholar to make some hypothesis about the measure of affinities, but it took much longer to actually come up with some mathematical expression of this. So someone very famous in the field of chemistry, of course, but not really credited to the field of chemical kinetics, is Lavoisier. So Lavoisier, he actually brought some of the first quantitative measurements or measures to chemistry, and also to affinity diagrams. So here you can see one of these examples from the work of Lavoisier. So this Mars symbol represents iron, the nabla, the upside down triangle, as I told you before, is water. This crossed circle, this is oxygen, and this triangle with the cross is nitrogen oxide. So he was looking at stoichiometry of reactions, which is basically the ratios in which things can react. But this was a very important contribution, because now things start becoming more and more quantitative. Apparently, there were some political reasons that Lavoisier also writes in a letter, that his theories, at least in this field of chemical kinetics, were not really accepted. But we won't go into that. If you want to read about that more, I can give you more details. So with the developments of Lavoisier in the second half of the 18th century, a very important concept was developed, which is totally obvious to all of us now, but at that time it was not, and that is the concentration of substances. So they started differentiating between reactivity and concentration. So you can, for example, sulfuric acid was at that time considered one of the most powerful reagents, right? Because it shifts other acids from their salts, and it's most strong because it absorbs most water. So that was really the time when people started looking at reactions between acids and metals in this period. So many scholars did not consider more metals as primary substances because they thought they were compounds of the alkaline parts. So it will take more than a century from here to really understand redox reactions. So let's go to a very important contribution from Carl Friedrich Wenzel. So he was a metallurgist that was working in Dresden, and he found the first link between reaction velocity and the concentration of reactions, right? So that's basically a qualitative description of the law of mass action. And so these are some quotes from his original paper translated to English. So what he was doing was making small cylinders from pure metals, so from copper, silver, lead, to have exactly the same sizes, the same volume, and then he would record or measure the weight of each one. And he found that that the times of these little cylinders to dissolve in different acids is very different. So that really was an important point, and it's, again, to repeat, is a qualitative description of the law of mass action. More progress was made by Claude-Louis Berthollet. He was a member of the Academy of France, and he was also the founder of the Polytechnique, École Polytechnique in Paris. And he collaborated with Lavoisier. But unlike Lavoisier, who was a young person trying to disrupt that field, he was a little bit more lucky in that respect. He actually went with Napoleon Bonaparte to Egypt, and he visited the Natron lakes, and he observed soda deposits in the limestone hills that were around. And he was supposing a chemical reaction between salt, so sodium chloride, and limestone, which is calcium carbonate, to produce soda, which is sodium carbonate, and the accompanying product, calcium chloride. So from these considerations, from these thoughts, he exposed for the first time in qualitative form the law of mass action in one of his famous publications, which is here on the right, this Essai de statique chimique, and where he showed that he said that the progress of a chemical reaction depends on the quantity and the conditions of the reacting substances. So Berthollet does not only relate velocity to concentration, right, and conditions, but also on the equilibrium. And that was at that time very controversial, but as we know now, that was completely right. Also, Berthollet, he made contributions in considering that for solids the chemical affinity remains constant. So then we move to Ludwig Ferdinand Wilhelmi. So what was important here? It's the introduction of the first differential equation in chemistry. Why is that important? Because differential equation tell you something about the change of a quantity. For example, here it's Z, right? It's the amount of a sugar versus time. And so time is introduced as a parameter. Up to this point in time, no one had really considered time as an important aspect. So Wilhelmi, he published a very important paper in 1850 on the kinetics of the inversion of sugar with acids. So we'll come back later to this sugar inversion, but basically you start from sucrose, and when you heat sucrose, which is just plain white sugar with a little bit of acid as a catalyst, it decomposes into glucose and fructose. So this was a very important reaction in the development of the first kinetics, because it was easy to measure and to quantify using polarimetry. So we'll later see that, of course, you can integrate this. Minus ms time. And so it's important to realize that Wilhelmi's work was done more than 40 years before Arrhenius, which is the one that we know, let's say, the most now. But it was really quite a big breakthrough at that time, but maybe not appreciated as it should have been. So two Norwegian professors that I want to highlight are Cato Maximilian Guldberg and Peter Waage, who are here shown in the same picture. Actually, they were also brothers-in-law, and they really were also one of the first to come up with a formula for the definition of mass action and volume. So they were representing F-chem, which they call the chemical force, and then M and N are quantities of some substance that will react, and they divide it by volume. So these are concentrations, right? And these, we'll see later, are kind of the order of the reactants, right? So they found that A and B, so these constants, with all the conditions otherwise being equal, depends on the nature of these substances. So we'll see, it can be first order, second order, or even in between, right? It doesn't have to be an integer number, as we'll see later. But yeah, they were the first ones to realize a kind of rate equation where there's kind of a reaction constant, concentrations to some power. So that was an important development. So in their work, they described the differential equation in the following way. So they found that the rate is proportional to some constant, right? The rate constant and concentration. But experimentally, they found this interesting relationship between the rate constant's dependence on temperature. So they found that T over T dash, right? So K at temperature T, so this is a certain K at a certain temperature T, and K accent at T accent depend on this factor M. So if we would convert this to a differential way of writing things, so dk over K would be M dt over T. So they found that this quantity M is constant for a given reaction system, so it will be different for any different type of compounds. But if you pick a certain reaction, this value M was a constant and only dependent on temperature. So they confirmed also what Van Hoff would later do, that M is this factor, or this function, of temperature in the following way. And so they found the dependence of M with temperature is, for example, where M is just A for the dissolution of metals with acids, M equals Ct, so the other factors are 0 for the decomposition of dibromosuccinic acid, and for example M equals B times or B over T for ethyl acetate hydrolysis with sodium hydroxide. So in most of the cases M appears as a constant, but also Harcourt and Esson, they admitted that in some cases it does not happen. So the hypothesis was not super strong at this moment. So now we come really to the start of the field of physical chemistry as we know it. And so these are some of the most influential people at that stage. So you see Arrhenius on the left, we have Van Hoff here and Ostwald here. And they started the journal, which is called Zeitschrift zur Physikalische Chemie, which means, the Journal of Physical Chemistry. It was first published in 1887 in Leipzig, and that really became a very influential journal in physical chemistry, and people started calling it also physical chemistry. So Ostwald, he's maybe less famous in chemical kinetics than Van 't Hoff and Arrhenius, but he has made a very important contributions in kinetics. So we talked a little bit before about this sugar inversion, and he was basically realizing, we'll see later this sugar inversion chemistry, that acid was a catalyst, so that it's not used up. The acid concentration in that reaction doesn't really change, but that was really a big realization, and it was the start of the whole field of catalysis. So that was, I think, a very important contribution of Ostwald to the field of catalysis. So Van 't Hoff, he was a Dutch chemist. He worked in the Netherlands and in France, and then later joined Ostwald in Germany. And he has done many very important contributions to the field of chemistry and physics. So he worked on the first principles of stereochemistry. He worked on the thermodynamic description of osmosis and solution dynamics, and he received the Nobel Prize for Chemistry in 1901. And so a very important contribution of Van 't Hoff is realizing that there's the ratio of constants of forward and reverse reactions. So he started realizing that there's something called chemical equilibrium. So Van 't Hoff, he found that the equilibrium constant, so the big capital K here, had a dependence on the absolute temperature, right? R is the gas constant, and C is just a constant. So he realized that the equilibrium constant depends on temperature, and it's different for exothermic and for endothermic reactions. Van 't Hoff called this mobile equilibrium, which is later more generalized by Le Chatelier, which is what we now know in chemistry as Le Chatelier's principle. And from this equation and the relation of the equilibrium constant with rate constants that he obtained experimentally, he found some relation of the rate constant with the temperature. But he had these parameters A and B. A was in some way related to specific heat, but B could not be determined. So he later on went to measure these A and B values for different reactions, but he never was able to work out exactly where these things fundamentally come from. So here we see the sugar inversion that I was talking about before. So you start from sucrose, which is table sugar. If you heat it with water and you put a little bit of acid, it can decompose into glucose and fructose. And why do people do that? So in the bakeries, they do this a lot because glucose and fructose together, they taste sweeter than just sucrose. And so what they used to analyze this is a kind of modern interpretation, but they used polarimetry. So you have light, you have a polarizer that makes just linearly polarized light, and then depending on the concentration of your species, your light will turn a certain number of degrees. So with a second polarizer, which you call analyzer, you can determine how much the optical rotation is. And so that's a technique which was available at the time of Arrhenius, which helped them to really spectroscopically measure this reaction kinetics. Okay, so Arrhenius then did a reinterpretation of K as the ratios of quantities of an active sugar and a total sugar and its temperature dependence. So this is really this important thing. So he was realizing or proposing that there was a total amount of sugar but there was only a small fraction which was in an activated state, right? And this is really been biasing the way that we now think about this. So with that, it's no longer necessary to have this A and B quantities that Van 't Hoff was talking about, because Q over 2 is half the heat of activation of sugar, and T is just the temperature. And so Arrhenius also successfully used this equation for describing acid reactions and electrolytes. So if we work this out a bit, we end up with the famous Arrhenius equation, which relates the rate constant to a frequency factor and the energy of activation. So this activation energy really comes from Arrhenius talking about active sugars, which are a small part only that are the ones that actually undergo the chemical reaction. So he introduced the concept of activation, but still the physical explanation of this activation was a bit vague at that time. So now we have to wait about 40 years to get new insights into what these constants in the Arrhenius equation really can mean. So there was a completely new field opening up, which was quantum mechanics. So two important people there are Michael Polanyi and Henry Eyring. So Polanyi was the director of the Haber Institute in Berlin, and he was hosting a young, at that time, Mexican American, which was Eyring. And he wanted to apply a quantum mechanical description of reactions. So they made a description for bimolecular gas reactions in a fundamental paper in 1931, where they calculated molecular at atom states during reactants using quantum mechanics. So they obtained bond and activation energies, and they were plotting the energy in a function of the distance between the atoms. And this is kind of the first diagram of potential surfaces versus reaction coordinates. So here you can see the distance between atoms X and Z, distance between atoms X and Y, and some form of a reaction coordinate going describing the reaction of hydrogen here forming hydrogen and boron, or bromine. So it's then Polanyi and Eyring that advanced even further the Arrhenius equation, and they were able to get absolute reaction rates statistically from probabilities of reactants rising from their fundamental state to the saddle point in the energy diagram, which is the activated complex, and then performing their reaction. So this is basically in line with the way we think about reactions now, is that we have a certain Gibbs free energy, we have an activation process, and then we have the transition state here going to the products over here. So they obtained that the rate constant is now a function of the Gibbs energy of activation. So here R is of course the gas constant, still temperature again, the Boltzmann constant and Planck's constant, and K is what's called a transmission coefficient that is in many cases considered to be 1. But we will come back in later classes on transition state theory. So in the most recent history of chemical kinetics, we have a number of key people: Kramers, Christiansen, Klein, and Nernst indirectly. So Kramers, he was a Dutch physicist. He worked in Germany and in Denmark, and he was an important collaborator of Bohr in the famous Copenhagen Institute of Theoretical Physics. So he developed an interest in chemical kinetics through a collaboration with Jens Anton Christiansen, that was also in Copenhagen University. So Christiansen, he visited the Bohr Institute after his PhD for almost 1 year, and he was really interested in treating the dynamics of specific chemical reactions. So in his PhD thesis, he introduced for the first time the term chain reactions, and he developed that field much more together with Bodenstein. That will really produce a definitive theory of chain reactions around 1950. So the new contribution of here in this diffusive stochastic theories is the addition that a chemical reaction is an intramolecular diffusion process. So two species, they have to meet in order to react. So Christiansen, he published 2 papers, one in 1935 and one in 36. So in the one of 36, it's very significant because Christiansen confronted Arrhenius' theory of activated state with a not very well known theory of Nernst at that time. Nernst, in Nernst's theory, so the reaction velocity is analogously to Ohm's law, and it's a ratio between chemical potential and chemical resistance. So Christian set out to demonstrate that what Arrhenius was describing and what Nernst was saying were basically the same. Later, Kramers and Klein put this on a more fundamental framework, so they really looked at the mathematics of these systems, of these diffusive stochastic theories. This goes a little bit beyond the current course setting, so I'm not going to discuss that in detail, but it is an important work of Kramers, the Klein-Kramers equations of such systems. If you want to read more in more detail about this introduction, you can read chapter 1 of this book, edited by Vivek Patel on chemical kinetics.